Hello everyone, my name is Peng Yunfei, and this is a presentation of my EECS4080 project. The project name is Optimizing Data Compression Using Clustering, and this project is supervised by Professor N. This is the outline of this presentation. First, I will give you a brief introduction of the whole project, as well as the objectives and the related works. Then, I will introduce the background information that are used and the methodology I used in the experiments and show you the results. In the end, I will give you my conclusion and the work to be done in the future. This is a brief introduction of the whole project. Data migration is a process of moving data from one location to another. To reduce the business interruption time, data migration needs to be done as fast as possible. To transfer data over the internet, data compression is commonly used to reduce the size of data and thus speed up the data migration process. This is the motivation of the project. To solve this problem, I chose clustering to see if it could improve the performance or not. Clustering divides a set of data points into a number of groups such that data points in the same groups are more similar to other data points in the same group than those in other groups. The objective of this project is to explore ways to group and reorder data tuples, like rows, in a relational table so that the size of data after data compression can be minimized, and to investigate whether and how data clustering can help data compression. In this project, different clustering methods are investigated. We try to find some related works on the internet, but actually, little work exists related to the project. No previous work investigates whether clustering could help to improve the performance of data compression, so the whole project is new. I will give you some background information that are used in the project. First, I will introduce the process of data migration. So first, a relational table is separated into few groups, and then each group of data is compressed individually by using compression algorithm called LZ4, gzip, or Z-standard at a different worker. Workers can work in parallel. And then the compressed data is sent over the internet to the other location in parallel. Finally, the groups are decompressed at the destination and put into the target database. As I mentioned, there are three data compression algorithms used in this project. The first is LZ4. LZ4 is an extremely fast lossless dictionary-based compression algorithm providing an extremely fast compression speed at 400 megabytes per second per core, and it is scalable with multiple core CPU. It also features an extremely fast decoder with speed in multiple gigabytes per second, typically reaching RAM speed limits on multiple core systems. And gzip is an algorithm for decompressing and compressing files on Unix-like systems. The basis of gzip is deflate algorithm, which is a combination of LZ77 and Huffman coding. LZ77 compression is a dictionary-based algorithm, using previously seen text as a dictionary. The last compression algorithm is called Z-standard, and it's commonly known by the name of ZSTD. It is a fast lossless data compression algorithm, providing high compression ratios. It gives a compression ratio comparable to that of a deflate algorithm, but faster, especially for decompression. And it also offers a special model for small data called dictionary compression. So all three compression algorithms we use is dictionary-based. Methodology I use to reduce the size of compressed data. First thing I do is to compress the original datasets with the 3 compression algorithms. Then I use k-means clustering algorithms to cluster each data file. K-means represents the numerical data naturally, and to represent text data, 2 text representation methods are used, which is TF-IDF and SPERT. Then I use k-means clustering algorithms to cluster each data file. Dictionary-based compression algorithms treat all data as plain text, like symbols, and k-means is good for symbolic data. Column-wise compression is used at the end, and we can treat the numerical and symbolic columns differently. The dataset we use are provided by our partner IBM, which is a 3 CSV data called DS001, DS002, and customer. The original size of the 3 files are 164 megabytes, 663 megabytes, and 2.48 gigabytes. And all contains both numbers and text. There are 8 columns in each file, 3 columns are numbers and the other are text. These are the performance without clustering. Throughput here is compression ratio over compression time. According to the results, LZ4 has the fastest compression speed, while gzip has the largest compression ratio, and this standard is somewhere in between. First, I use k-mean clustering, which is the most commonly used clustering algorithm. The process is, first given k value and k initial cluster center points, assign each point to its nearest cluster center. After all points are allocated, recalculate the center points according to all the points in the cluster, and repeat this step until the centers remains the same. In the experiments, I use 5 centers. There are 2 ways I use to represent text in k-means. First is TF-IDF. It can reflect how important a word is to a document in a collection. The TF-IDF value increases proportionally to the number of times a word appears in the document. And the next method I use is text embedding. It represents a piece of text using a vector of real values representing the semantics of this text. These are the result of k-means clustering with TF-IDF. Unfortunately, the compressed size and the compression time of all 3 files increase a little bit, but when it comes to larger file, the compressed time decreases significantly. And then I do a k-means versus random split experiment to investigate whether clustering have advantages over the random split of a data file. In the k-means clustering, I've used 5 clusters from k-means, and in the random split, randomly split the original file into 5 parts by rows. These are the results of k-means versus random split. Although some of the compressed size is smaller than random split, the difference between them is little. The dimension of the matrix after using TF-IDF is too high, like 4 million in my experiment, and SPERT is a text-embedded model and has lower dimensionality, like a few hundred dimensions, 769. So I use SPERT instead to see whether it can improve the performance. These are the results of k-means with SPERT. The compressed size are almost the same as original ones, but there are some tiny improvements in the compressed time, which makes sense because the text embedding can lower the dimension of the matrix. Then I use k-means clustering. It is a clustering algorithm for symbolic data, and it uses J-card distance. We treat the data in tuple as a sequence of text when using k-means. The purpose of treating all data as text is because our data compression algorithm is dictionary-based, which treats all data as plain text. These are the results of using k-modes. The compressed size are similar to the k-means, but there are some significant improvements in the compressed time in all three files. At last, I did some column-wise compression. I noticed that there are two types of data, and I can separate the columns by their data types and then use different compression algorithms to compress them. And finally, combine the two parts together in order to see if there are any improvements. We can simply use the throughput as a result to compare. The higher, the better. If we use LZ4 for text part and gzip for number part, the throughput is almost the same as gzip, so it's a valuable method. For a bigger file, if we use LZ4 for text part and gzip for number part, the performance is almost the same as gzip as well. For a much bigger file, if we use LZ4 for text and gzip for number, the performance is almost the same as the best performance of all three compression algorithms. The second type of column-wise compression I used is to separate the files column by column and then use different algorithms to compress the data. These are the results of the second type of the column-wise compression. In the last column, T or M means total size or max time used. Compared to the original compression, column-wise compression has a lower compression size or compression time, even if we sum all the compression time together. These are the results by using gzip. For gzip, the performance improves significantly as well. If we have multiple workers that can work in parallel, column-wise compression is a way to reduce the size of compressed data. These are the conclusions of the project. Using k-means does not have an obvious improvement compared to the original data compression. But using k-modes doesn't decrease the size of the files, but it can increase the compression speed and decrease the compression time. Separating by column before compression is an efficient way to improve the performance. And compared to separating the files by data type, separating them column by column has a higher compression ratio and faster speed. For work needs to be done in the future, we only use k-means and k-modes in our experiment, so we need to find other clustering algorithms and test it to see whether it can improve the performance. And second, we can find and try different ways to order tuples. And finally, which is the most important, we have to see how the three compression algorithms works, and we can change the method to match the compression algorithms accordingly. That's the end of my presentation. Thank you for your time.